encode that as a reflecting spectrum, right? Where the troughs are the wavelengths at which the material was absorbing photons, and the peaks are the wavelengths at which the material was not absorbing photons, right? And that's the fingerprint of the chemistry of the target. And then, we just went through this, and we just got each kind of section, right? The stream of photons, it's bounced back off the surface of the planet. I showed you how to work this out, right? I alluded to how you would calculate the dilution of that signal as it moves from the sun to the planet. We spoke about how it interacts. Remember Beer's law and Snell's law and all that sort of stuff, controlling the selective absorption of photons. The stream of photons that don't get absorbed get bounced back, and we encode that as this derived SI unit, spectral radiance, which is units of optical units, radians per micron. We then said we're interested in making spectral maps of the surface of planets, right? So we have this sampling system, which is the spacecraft looks at each patch of the ground and samples the spectral radiance from that patch, that patch, that patch, that patch, that patch. Forward motion of the spacecraft, it just repeats, and in that way it builds up a two-dimensional map of, if you like, the number of photons reflected from each patch of ground at each wavelength, right? And we split it up into the different wavelengths or colors using some kind of spectrograph after we've sampled the light with a telescope. It focuses that onto a detector. In here, some magic happens where we turn photons into photoelectrons, we convert that to some kind of charge, we digitize the charge, and then tomorrow, in tomorrow's lab, you'll start exploring data where you'll start looking at satellite images, which are basically this. So for each wavelength or color that the spectrograph split the light into, in each pixel, where a pixel corresponds to an area on the ground that the spacecraft sampled, you have a digital number, and we can relate that digital number all the way back to the reflectance and the spectral radiance and the number of photons that left the ground. Okay? People happy that they understand how remote sensing works? Mm-hmm. Yeah. Okay, so today I'm just going to give you a demonstration of how we would make these kind of reflectance measurements. Right. So all I've got here is and you can come closer if you like, so you can see this stuff. Right. So what have I got here? We have. I'll drag your chairs over a while. So I have a series of targets. What appears to be grab a seat, honestly, there's a seat here. So I brought a series of targets. We have a leaf that appears to be kind of healthy. We have a leaf that doesn't look healthy at all. And then we have a leaf that's, I don't know, halfway in between, right? So these were just out of whatever that plant is outside the front of the post building. We also have some what you might call standards. So I just printed off a bunch of these things. I just went to my printer and I printed off something that was blue, pink, magenta, green. So remember the color wheels that we had where we had the intersecting colors? Cyan, yellow, red, black, and then some different types of blue, right? So this cost me virtually nothing to do. I then have something that photographers use to calibrate their cameras. This was $500, I think. Piece of cardboard with some colors on it, right? But they went into more effort making this than I did making that. And then finally I have these things. I have these things, which are reflectance standards that we actually use in for doing these measurements in the lab. So NASA uses these, the European Space Agency uses these, we use these as part of our research. So I have a white one, which is a white target, right? This is about $350. And we'll show you a bunch of these. I have a black one, right? Why does it look black?
It's absorbing everything.
Everything, right? All the light that's coming from this light are being absorbed by whatever that's made of, right? Why was the white one white?
Reflects everything.
Right, at the wavelengths we can see, right? Our eyes are sensitive to. So on and so forth. Blue one. So in here I've got blue, red, green, yellow, black, white, and then I've got another one, a mystery one that we're going to work on towards the end of this. Right. But when we're doing these measurements, we use these to calibrate the spectrometers. I'm just going to quickly go upstairs and grab one last thing that I forgot. In the meantime, the marvel of the technology before you.
That's one of that, my phone. Thank you. KC Anatolia.
Okay, so I've got some targets, some cheap, some expensive. So if we look at this, I've got this, right? To make a reflectance remote sensing measurement, I need a signal, right? So what I've got is this. This isn't laser light or anything, everybody can see there's a light coming out of that, right? This is a tungsten halogen lamp. It's kind of stable, you have to heat it up, but once it's heated up, its output doesn't vary, right? So if you remember in remote sensing, we're shining sunlight on the surface of a planet. If the sun shone and dimmed, then we get a very different number of photons leaving the sun, which would mean a very different number of photons being reflected from the planet's surface, right? So we can't have that, which is why we need a stable light source for these kind of measurements. That was about $2,000.
Is that also like a black body?
No, this doesn't approximate a
It's
black
not
body.
like that.
So it's a
It's not
tungsten
like-
halogen lamp. So
Oh,
you can
halogen.
get different types. You can get a tungsten quartz halogen lamp, which more closely approximates the sun's spectral output. But that's a good question. For the purpose of this, we're not trying to replicate the sun's output. We're just trying to have a known and stable illumination source. Right. And then I've got a spectrometer. Right. So this was about $8,000. So this is a little spectrometer, and that is this thing here. Okay. And in it there is a detector which converts a stream of photons into a digital representation of that analog signal, and I'm going to show you some spectra like that we're going to collect using this apparatus. The one thing we're not mimicking is this, right? We have no telescope here. What we're going to use instead is a fiber optic. So what I'm going to do is connect this end to the light. So just a fiber optic. So I'm going to connect that in here. This then goes into the spectrometer. And then this end is, if you like, the telescope. So again, this isn't laser light, so to say, people can see, right? So the light comes out of the spectrometer, goes into here, comes out here. That illuminates the target, the light that gets bounced back goes back into the optic and comes up via the other leg into the spectrometer. Right. So we have a light source, we have a spectrometer, we have some targets, and then we have a method for collecting the light. So what's in this box? So you pronounce that Zerny Turner. Right. So if you look at what we've got here, so that's a kind of picture of what it looks like, and then on the left is just like a half-assed ray trace that just shows how light's moving around in the system. So we have light from the target, right, which is coming in from all directions, right? In this spectrometer, and in most spectrometers, you have a slit, and a slit is exactly what it sounds like. It's just a slit. So it's just a gap cut into metal. In this case, it's 10 microns or 10 millionths of a meter from side to side, right? So that's the slit. You've got light coming in from all directions. The purpose of the slit is to reduce well, there's several reasons. One is to reduce the angle over which you're receiving light into the spectrometer, to try and keep it from as narrow an angle range as possible. In spectroscopy, the narrower the slit, the higher the spatial resolution, right? In this case, the spectral resolution. It just means you have a narrower beam, right? Can you imagine what a narrower slit also does? If I make that slit really big or really narrow, what does that do to the amount of light that the spectrometer collects? How about if I make the slit nothing? How much light would enter the spectrometer? 0, right? So the narrower I make the slit, the higher the spatial/spectral resolution, and I'll describe that, I can achieve with this spectrometer. But the less light I emit, so my signal to noise goes down. The wider the slit, the more light I emit, but the worse my spectral resolving power. Right. So again, this is part of the spectrometer design process. So we get light from the target, I pass it through the slit. From there, we've still got bundles of rays going in different directions, right? So the first thing I want to do is collimate the light, or make the rays parallel. So for you astronomers, you can assume that the rays are parallel, right? Because the target is so far away from you. So light rays aren't diverging or converging. When we're imaging something, we also want to collimate the light. But we can't rely on nature doing that for us because the target's so far away. So we have to use a mirror or a lens. In this case, there's one collimating mirror, which would be this one, and it's just a concave mirror. Right. So that parallelizes the rays of light. Now we're going to split the light, and we do that with this flat diffraction grating. So you can have a look at that. This is actually a bit beat up, but this is a diffraction grating. This is a couple $100 or something like that. It's not a very expensive one. But if you look on that side, you'll see a rainbow of colors. Much better than a CD. You know, I point to CDs, and we've got one on the table there, but it's kind of round and kind of crap. If you kind of tilt that, you'll see a rainbow of colors appearing. So that has basically very finely ground parallel grooves in the surface. And it's those grooves, you remember I showed you that sawtooth picture. It's the spacing and the angle of the facets which cause light of certain wavelengths to be scattered in different angles. So the diffraction grating that's in here is not dissimilar to that one. Right. Obviously that's cheap. And okay. If you notice on the side, it says 500 microns and nanometers on one of the edges. That's the blaze wavelength. You remember I said you can only make these things really efficient for one wavelength. So in this case, it's blazed at 500 nanometers, which is like visible greenish light, because we're interested in making visible reflectance measurements. Okay. I don't know what happened to that. It looks like somebody sanded the surface of it. Maybe it's just the coating that's breaking down or something. But anyway, one of these is right here. Right? So we have a diffraction grating. It's just like it. So that's this thing over here. And as it shows on here, the diffraction grating splits the light into its different colors. Right? We then bounce that off in a different direction to a focusing mirror, which is just another concave mirror. And that focuses the light onto the focal plane array. And you'll see the red light is focused in one location,
the green in another location and the blue in another. Now really we have a wavelength of colors because this is a high spectral resolution device. So basically we're focusing light of one wavelength or photons of one energy onto one pixel in this focal plane array, and then another wavelength onto the next, and another wavelength onto the next, right? So that's what I'm talking about, spatial and spectral resolution. So in this case, the focal plane array in that device, there are two types of focal plane arrays that are commonly used in reflectance spectroscopy. One you'll have heard of, a CCD array. So you've heard of a CCD array, charge coupled device, right? The other that I think is now kind of, they use them in phones, is a thing called CMOS detector. CMOS stands for Comprehensive Metal Oxides Semiconductor, right? In terms of like the physics, they work in the same way. We've got a light-sensitive crystal, which has either an excess, it's an alloy, has either an excess or a deficit of a dopant, which has more an excess or deficit of electrons, right? And we shine photons of a particular wavelength, and that can cause loosely bound electrons to be boosted into the conduction band, and then in the presence of a bias voltage, we can sweep them up, and that's our signal, right? The difference between a CCD and a CMOS is, you remember I said, we're generating this flux of electrons, of photoelectrons, and the bias voltage is whizzing them around. We've got to kind of, we're converting photons to photoelectrons, and we've got to assess what the charge is, right? Because we're filling that bucket. Remember, beneath every pixel in the array, we have a silicon integrated circuit. And that circuit basically comprises a transistor and a capacitor, a gate and a bucket. During the integration time, we're going to allow photoelectrons to fill the bucket. The more photons that strike that pixel, the more photoelectrons will be in the bucket. Right? Remember that? So with a CMOS detector, there is a gate and a bucket beneath every pixel in the array. Right? So every pixel in the array has its own gate, bucket, an amplifier, an AD converter, actually beneath the pixel. With a CMOS detector, they kind of whiz it all off to the end, and they do it at the end of the column or at the end of the row. Right. But that's the difference. In terms of the physics of how they transduce photons into photoelectrons, it's exactly the same. For this device, we don't have a two-dimensional array, right? So your phone has a two-dimensional array, because when you take a photo, you get an image, right? This has a one-dimensional array. So the focal plane array here is 1 pixel high and 2048 pixels long, right? And the 2048 pixels are spread in this direction here, which is why each pixel collects photons of a different wavelength of light, right? Because we're dispersing the light in this direction, which is the long axis of the array. So that's how this thing makes a spectral measurement. The other thing is this order separating filter. If you remember I said with these diffraction devices, the rainbow repeats and repeats and repeats and repeats. Most of the energy, like the interference patterns that you've probably all seen, most of the energy is in the big blip in the middle, right? But then we have those kind of limbs and those bumps on the edges where we have the second order dispersion, and we need an order separating filter so that we don't count that light, right? Because we're trying to count photons, and if we're counting more photons than we should count, then that's bad. Right? In this box as well, it's not shown here, but this is what's called a folding optical design, right? You see, we're folding the light up in here to make it small, right? The problem with these folding designs is that you can have a lot of what's called straight light. So we've got light bouncing all around in this place, right? And you've got to be careful that light that you don't care about, you don't want that hitting the focal plane array, right? You really just want there to there to there to there to there. But if you've got light from here which is somehow getting in, or light from here which is somehow getting in, or from here, that's bad, right? And you call that stray light. So how do they mitigate stray light in these devices? They paint the inside completely black with a highly absorptive material, right, to basically stop these secondary reflections. They also have things which they call baffles. So when you break one of these things open, we're not going to do it today, people have carved out like semicircular embowelments and things like that to basically trap photons. So if you have a cup-shaped piece of black metal in there, and this is predicted, right? An optical engineer predicts likely ghost images or stray light. And if you say, well, there's going to be a load of light hitting this surface of the spectrometer, And some of that is going to bounce in. What you can do is put a cup-shaped thing here to kind of trap those photons, get them bouncing around multiple times within a cup-shaped thing. And by doing that, you can create a cavity and no photons will escape. Right. So this is a folded design because we want it small. You can unfold the Zerny-Turner spectrometer to reduce these stray light effects, but then you end up with a physically bigger spectrometer. Right. Does anybody have any questions about this? Yep.
On the model on the left,
Right.
when it hits the focusing mirror at the end, it has the.
This is just a cartoon,
Okay.
remember?
Yeah, the light goes out. So it in real actuality, it goes into itself when it goes to the focal plane array. So
The light goes from here to here and then
And
goes to here.
yeah, but when it goes to there, the light is like increasing
It's
in
dispersed, yeah.
dispersed. On the other one on the right, it's like looks like it's concentrated.
This one here.
No, sorry. On the like.
Oh, right, okay, well, this is just a cartoon.
Okay, just make
Right.
sure.
Point is here, we collimate it so that we can diffract it predictably, right? And then it moves to here, and then we want to focus it onto the focal plane array, because we're relying on the fact that the red will land on a particular pixel and the blue photons won't land on the same pixel. And then we have dispersion from short wavelength to long wavelength in a predictable way.
I think you mentioned this last class when you were going over the order. So is there ever a time where like the first order and second order reflections, like they overlap if each one is, like if you get too much signal, and how do you correct for that in that
So
situation?
you correct for it using filters. So it's usually the long wavelength of one order overlaps with the short wavelength of the second order.
Right.
So they kind of, you've got, let's do it, blue, green, red, blue overlaps with the red, green, red, blue overlaps with the red, green, red. Now one way you can limit this order sorting effect is to look over a narrow wavelength interval. The broader the wavelength interval over which you diffract light, the stronger this order separating problem becomes. You get rid of it by using filters to throw away the wavelengths. And then again, cartoon. This is the order separating filter, and it just sits right on top of the focal plane array. So there are tons, we're not going to go into it too much in this class, but there are many, many ways of designing spectrometers to take light from a target, split it into its different components, and then focus it onto a focal plane array. Right? This is a common spectrometer design in these what we call point spectrometers. So this is not an imaging spectrometer, right? It's not like your phone. I point this at something and I get one spectrum. Now certainly if I wanted a spectrum of something next to it, I could just point the fiber optic in a different direction, right? But it's not imaging, it's a point source. For several reasons, mainly color aberrations, the Zerny-Turner is not used in imaging spectrometers, use a different type. So I think called a Dyson, which is not just a vacuum cleaner, is also a spectrometer design that's often used in imaging spectrometer, something called an Offner spectrometer. And the thing about these is always this thing, you want to make it as compact as possible without generating hellish stray light problems and maximize signal. Okay, so that's how that works. So now we will turn things on. So do I have everything on? Okay, right, everybody see that? So it's a spectrum, right? But it's not a reflectance spectrum. So what do we have here? On the x-axis we have wavelength in nanometers plotted, right? And what do we have on the other?
Intensity.
In counts, right? So that's basically dn. So sometimes you see counts, sometimes you see digital counts, which would be DC. Sometimes you see digital number, which would be DN, but it's all basically the same. That's the digital representation of the amount of light that that spectrometer is collecting as a function of wavelength. So, the light coming out of this thing is fixed and invariant in time, and I know its composition. That light's coming down this leg of the spectrometer, and it's being fired out of the fiber optic at the probe end. And that's happening on the outside. So if you see there's an annulus here, right? You see there's an annulus there, and it's bright on the outside and dark in the middle. So the return leg is the fiber optic in the middle, right? So that's the light that gets bounced onto that surface is transmitted back to the spectrometer, and that's what we see here. Okay. So, I said we've got to try and keep observation conditions constant, and that's why we have a sun-synchronous orbit, and that's why we convert to this normalized reflectance variable. You mentioned it the other day. You've got these bell curves, and they're changing. So at the moment, that's stable. But if I point at my hand's pretty absorptive, right? So the composition of my hand isn't changing, but as I wiggle that around, I can get the amount of light the spectrometer collects to vary. Not so much as a function of wavelength, but it's going up and down, right? If I point at this, so that's black, I point at that, I get something else. But I have to kind of control the way I'm making this measurement, right? Because otherwise I'm not going to get a repeatable measurement, which is the essence of science, right? If I go over the surface of a planet and I make a measurement of the stuff that's in that 10 meter square pixel and I derive a spectrum, the next time I go over that same point, I need to be able to derive the same spectrum, right? Or I need to make sure that the way I am making the measurement should allow me to derive exactly the same spectrum within the noise if what's in that 10 meter patch of ground hasn't changed, right? So another way of thinking about it is if I'm interested in change detection, I need to make a valid measurement such that I can say that change is real and not because I'm doing this kind of thing, right? So it's just the basic of scientific method. Right, you need signal over noise, you need repeatability. Right. So, we used to do this outside, but anybody guess what those peaks are? So remember, this is showing me how much light is coming into the spectrometer.
Is that from the composition of like the tungsten light?
No. So that's something else. So certainly what you see is it has the signature of the light imprinted on it.
Yeah, but the wavelength is strange. I guess disregard the wavelength.
So what is that?
The 600.
The fluorescent
everywhere.
lights.
Yeah.
Right, so
Wow.
I'm seeing the signature of the fluorescent lights.
Wow.
But again, it's not very good spectrometer, right? I can make that kind of,
Short
the wavelength of these features doesn't change so much, but this is not a good spectrographic system. Right.
I guess it's invisible.
So does anybody know how fluorescent lights work?
We should know, but forgot.
So that's kind of what we're looking at, right? And this is the one I just made upstairs in my office, right? So the way a fluorescent light bulb works is, you've seen them, right? They're these big long tubes, and you put electricity in at one end. And in it, has anybody ever bust one open? It's vaguely fun. So you take one of these tubes and you smash it open, you hear a pop, and you get a cloud of powder that comes out of it, right? So the popping sound is because there's a pressure of gas inside these lamps. It's mainly it's mercury vapor, so don't snort it or anything like that. Mercury vapor with an inert balance, which is usually argon, right? So a noble gas, which is just a balance. And what happens in these lights is you feed electricity in, and there's a tungsten element which heats up, right? And that energy that's radiated collides with the mercury atoms in the mercury vapor, and mercury characteristically absorbs light and re-emits it in the ultraviolet part of the spectrum, right? So all the way down here, right? Now we can't see ultraviolet light, right? So mercury radiating ultraviolet light from here doesn't help us with a lighting problem. So when you bust one of these things open and you get this puff of white powder, on the inside of the glass, they coat it with some rare earth metals, right? The rare earth metals absorb the UV photons emitted by the mercury, and then they re-radiate photons at a longer wavelength, which is fluorescence, and that longer wavelength is a visible part of the spectrum, which is why these things generate light, right? So the tungsten element causes excitations in mercury at a wavelength we cannot see. Those photons strike what they call the phosphor, these rare earth metals that are painted on the inside of the tube. When you get this down, you'll see the tube looks white, and what you're seeing is these metals painted on the inside. Those UV photons excite electrons to jump away from where they normally reside in those metals. When they relax back down, they emit photons of visible light, and that's how we generate light. And it's called fluorescence because the re-emission takes place instantly, but at a longer wavelength. Right. Phosphorescence is different. That's like glow in the dark stuff. So that's when you shine photons on something, and you boost electrons to you produce a population inversion, a bit like a laser, except it's not coherent. And you boost electrons into a metastable state, and then when you turn the light off, those electrons slowly fall back down to their natural state, and in doing so, they radiate light at a longer wavelength. But that's, fluorescence is instantaneous, phosphorescence is glow in the dark. So you take the light source off, you still get emission. With fluorescence, you turn the light source off, and it stops emitting instantly. Okay. So this is just something I grabbed off Wikipedia. So I'll put this on. I haven't put it on yet, but I'll put this on the Loudlima thing at some point. But these are just the features. So do you agree that this spectrum that I just casually took in my office yesterday looks very much like this spectrum, which I just got off the interwebs yesterday? And all this did is they just mapped on which element these peaks correspond to, right? So we've got some mercury down here. We've got a thing called terbium, which I know not much about, and another thing called europium, which I know not much about, but here are some pictures. And then finally, we've got some argon features out here, 21, 22. Right. So if you like, we've just done some spectroscopy, right? We've just identified the chemical elements in a fluorescent lamp, right? Same way that you can identify the chemical elements in the atmosphere of an exoplanet or in the atmosphere of our sun. Same way. Here we're looking at emission features, not reflectance features, but things emit and absorb and therefore don't reflect are basically the same wavelengths. There's some subtle differences in the wavelengths, so things don't exactly emit and absorb at exactly the same wavelength. There's some very subtle differences, but basically they emit and absorb at the same wavelengths. And everything on the periodic table has its own unique wavelength at which it emits and absorbs photons, and that's just all that we're seeing in here. Okay. Right. So let's go back to this. Okay, so I'm just going to point out a few targets now, and we're going to do some half-assed spectroscopy. So if I point at white, what do you think is going to happen? What do you think the shape of the curve is going to be if I point this at the white thing?
High intensity element.
High intensity. What kind of shape might the curve have?
It'll be like really big, but it'll still have like peaks in those wavelengths.
Right, so that's a good answer. It won't be flat, right? Because this is digital counts. This is not reflectance yet, right? So it's going to go up. I think we're going to see that these things kind of disappear because we've got so much light coming in, right? Also, I'm not pointing at them, right? When I point at them, I get that. But when I point away from them, I'm getting a much more diluted signal of the light that's coming directly from the lamp. Certainly, that light is coming down, hitting this target, and will be bounced into the spectrometer. But when I get close, the signal the spectrometer measures is going to be swamped by the photons that come out of the light source leg of this chain. But yeah. Okay, so if I do this, I get that. So what do you notice about the scale on the left-hand side? What does it go from and to?
From 0
To roughly?
45.
No, the whole range.
Oh,
go from 0 to 60.
65,000. Do you remember that thing we spoke about, radiometric resolution? The ability of a spectrometer to distinguish subtle variations in reflectance, right? And you remember I showed you that picture of 8 bits, right? And what was 8 bits? Do you remember what 8 bits was in terms of the measurement range?
2 to the 8.
Right? 256, right? If I have my 8 bits, and I go from 2 to the 7 down to 2 to the 0, and I turn all the bits on, then I can generate the number 255, which including 0 means I have 256 variations in brightness that I can measure. And that was an 8-bit system. Do you remember what a 16-bit system was, vaguely?
65,000.
Right, so it's about 65,000, right? So this is a 16-bit system, or the analog digital converter in a spectrometer quantizes, right? Quantize means to break up into small pieces. Quantizes the incoming signal into about 65,000 different levels of brightness, right? Where 0 is none, and 65,000 is the top, right? A lot of spectrometers use that, although in satellite data quite often people use, that would be an unsigned 16-bit integer. Unsigned means I only have positive numbers. It goes from 0 to like 65,000. I can take the same 16 bits and I can split them down the middle, and I can go from minus 32,767 to plus 32,767. And sometimes scientists use that because they use the negative range to store metadata or flag values, right, or bad data values or something like that. And typically 32,000 is more than enough brightness levels to encode the brightness coming from a target. Right. Okay, so it's a 16-bit system, and remember, the light from these lights is kind of weak. The light from that light is kind of strong. So what do you notice? I'm going to try and go straight down. What do you notice? What's happening as I move this thing closer and closer to the white target?
The light from the gas lamp on the table is taking over compared to the reflectives from that.
Right. And if I get really, really close, what happens to the curve as well?
Reflects more.
Right, so the spectrometer is measuring more reflected light.
Yeah.
Right, so more of the light, two things. First, the light from the lights is kind of being excluded and overwhelmed by the light from my lamp source, right? And the closer I get, the more light is being reflected back into the spectrometer lake, right? What's happening? Right, so as I get closer and closer, what just happened? At a wavelength of about 700 nanometers.
It exceeds the number of counts.
It exceeds the dynamic range of the instrument, right? You see that flat bar at the top? See, it just flattens out at the top, right? It hits 65,000 and it just reports 65,000. So that's a saturation value, right? So if you like, in this state, I don't know how much light this surface was reflecting at 680 nanometers. I know it was at least equivalent to 65,000, but I don't know what it is, right? Whereas at 420 nanometers, it's about 15,000 counts, right? So we call that saturation, right? The detector is just saturating because it's being overwhelmed by photons. Okay. So when you're designing instruments, and we'll show you, we'll talk about this in a few weeks, when you're designing instruments, you need to avoid saturation, right? For you astronomers, you're not saturated, right, because you're counting 3 photons or whatever it is, right? But we can end up in this situation where we're counting too many photons, right? And the way saturation works is, say we have our photosensitive material, photons, photoelectrons beneath each one. In a CMOS detector, we have a bucket and a gate. We open the gate. We open the gate for the integration time, right? So while it's open, photoelectrons are filling the bucket capacitor, and the bucket fills, right? What you just saw is when the bucket gets full and it can no longer take any extra electrons, right? Now, in this part of the spectrum, they call that the electron well depth. So the capacity of a bucket is referred to as the well depth, and each bucket can contain a certain number of photoelectrons, right? Typically in this part of the spectrum for these kind of detectors, that might be something like 10 to 30 million electrons. But in a few weeks, I'm going to show you how you compute the actual number of electrons, and you can work out whether you're going to saturate or not. Okay. How might I reduce the problem of saturation given what we've just said? So if I keep this here, how could I stop that happening?
Increase the resolution.
Couldn't go like,
Weaken the light is one thing, right? So I can certainly do that. Now I can't weaken, in a remote sensing situation, I can't weaken the strength of the sun, right? But if you think about what did I say at the beginning, which was governed the amount of light that was emitted to the system?
put a filter, just like,
So I could reduce the slit, right? But that would have impacts for the spectral resolution, right? Which the scientists might want to keep constant, right? Remember the science traceability matrix. As engineers, you can't just do what you want, right? One thing I can do is use a filter, right? So if I do my modeling, my performance modeling, I work out that the sun and the reflectance is always going to leave me suffering from the saturation problem. I could just use like a neutral density filter, right, to throw away some light. Okay. The other thing I could do in a design is I could decrease the aperture of the telescope. So if you remember in that picture that I showed, we have our ability to resolve detail on the ground is based on the size of the detector, which we usually do not change, and the focal length of the telescope, right? So a longer focal length means I project that detector via the optic down to the surface of the planet, and the light doesn't spread that much, it stays tight, which means I have a small pixel on the ground, right? At the same time, that's a problem because that small patch of ground isn't reflecting as much light as a large patch of ground. So to buy back sensitivity, I might increase the size of the telescope, or the diameter of the lens, or the diameter of the optic to collect more signals, more photons when it comes up, right? So one thing that I can do to reduce the number of photons that my telescope absorbs is to use a narrower diameter optic, right? But the way we usually do it is by varying, so I'll just show you how that might work. So one way, so I'm saturated now. Now this thing here is just an aperture stop, and it's just like a piece of metal that goes up and down. Right, so I just basically, I turn the sun down, or I reduce the diameter of the optic, right? And now I don't have my saturation problem, right? What I do have now is a signal to noise problem, right? Because I've thrown away a lot of light. So we don't usually do that. Oh, bollocks. What's the other thing that we can, the other thing that we've been speaking about now, we're speaking about in the context of electron wells, and what's another thing I can vary in this design? To reduce the number of electrons I collect such that I don't saturate. It rhymes with integration rhyme.
Integration time.
Right, integration time. I can vary the integration time, right? I can keep the gate open for less time, thereby collecting fewer photoelectrons, thereby not filling my bucket or exceeding the well depth, right? So what I'm going to do now is, this is just an expensive block of metal. It's about $700. The purpose of this is it just keeps everything straight. So instead of me doing this, right, and being all over the place, I just put this in here, and it's just a block of metal with a couple of set screws on it. Right? So if I put the probe in here, get it to about the bottom, and then just use the set screw, then that will kind of keep it in place. Right, so that's just normalizing my illumination. Right. So via this piece of software, I can find it, I can vary my integration time. So this is kind of small, but you see there I've got a couple of things. So integration time here, right? So, and that's in milliseconds, and I can't remember what the possible integration times on this spectrometer are, but if we just play this in minutes, you'll see it's in milliseconds. So if I make that 200, what's going to happen to the curve?
Is it gonna get bigger?
It's going to get taller, right? Because I'm going to set the integration time for long. I'm going to double the integration time, which means the gate is open for twice as much time, which means normally I'm going to collect twice as many electrons. Right. Okay, so I just saturated. So 100 gives me that. But here I'm sacrificing signal, right, on some level. I really want to collect as many photons as I can to give myself a higher signal to noise ratio. So I don't want to leave photons on the table, so to speak. So, you know, I could just play with that. I could make 150. Yeah, I still got some saturation. 125, split the difference. Not bad, right? So now I'm using most of my dynamic range, right? So any measurement has a range or a dynamic range. Right, so if I'm interested in measuring subtle variations in the brightness of targets that I illuminate in terms of their reflected light, if I have my dynamic range as 2, 0 or 1, then I can say it's bright or it's not bright, right? And there's no information there. The larger the dynamic range, the more number of bits I encode there, the easier I can identify very subtle peaks and troughs in this curve. Right, so I kind of want to maximize that signal, but I don't want to saturate, because if I saturate, I have nothing. Right, I have these flat plateaus where I really don't know how much light is reflected. Okay. This desktop spectrometer, these are used for things like you know, production lines where they're making pills, like pills, medical pills. One of the ways that they can monitor the purity of the pills is to pass them under a device like this and just make sure that the curve looks the same, looks the same, looks the same, looks the same. And if the curve changes, that means there's a problem with the composition of the pills, which is being manifest as a difference in the reflected light. So that's one industrial application that these things are widely used for now. Right. But in that case, they have a bit more time. So you'll see here, this is running at that integration time of 120 milliseconds. What do you notice about this curve? Is it stable or is it flickering? Is it changing? Flickering, right. And that is stable because I paid a couple $1,000 for it. That's not changing, right, because I put it in my metal block. So what are we seeing here? What is this flickering?
From the spectrometer?
Right, it's just the inherent noise in the spectrometer. Right, all instruments are noisy, you never get a precise measurement. The precision is basically how much it's flickering up and down. Okay. And all spectrometers have this, and this is the noise in signal to noise. Right? The signal is, if you like, the average position of that curve, and then the noise is how much it varies up and down from that average. So with these spectrometers, I can do things like this. So, well, actually, let's make that 20. So I'll have a whoop. No, I made it. So on these spectrometers, you can average the number of scans. So if I make this 50, right, so it kind of got less noisy, right? I still have this kind of sawtooth pattern, which is basically part of something related to the material, but you'll see it's not going up and down as furiously. It's closer to the average because I'm just averaging scans. Right? There are some techniques you can use in satellite remote sensing missions of planets that achieve this effect, right? And the way they would do that is, if you imagine I want to measure 10 wavelengths of light, right? And if you imagine I have a focal plane array which has, I'm picking a ridiculous number, it has 100 pixels in this direction, right? And this is the direction the spacecraft is moving. On top of those 100 pixels, if I put 10 filters, one for each wavelength, and each filter covers 10 pixels, right? Then as I'm moving along, I get 10 measurements of that patch of ground at each wavelength for each pixel at the same wavelength, right? And because I'm moving in this direction, it's kind of a rolling kind of average. what I can do in that case is I can take 10 measurements, add them, divide by 10 to produce an average for each strip of the ground, right? And that's a technique that's called time delay and integration, or it's one way of doing it. So it's a way of, if you like, boosting your signal by increasing the apparent time you're looking at each patch of the ground. And it achieves something kind of similar, it just beats down some noise for you. But we'll change this back to 1. So we usually don't do that.
It might have to wait for the final average.
Yeah, actually it's just doing one, isn't it? Yeah. All right, so we're back to where we were. Okay, so when you're designing spacecraft, and we'll show you this, right? One thing we're going to work out in the future is we're going to take light photons from the sun, we're going to cascade them down onto the surface of the planet, we're going to take a target, we're going to work how many get reflected back. We are going to, based on the orbital velocity of the satellite, we're going to work out how much time we have available to us to make measurements from that patch of ground and that patch of ground and that patch of ground, right? We're then going to work out what the maximum integration time we have available to us is, and that's the parameter we're going to tune in this model to make sure we don't saturate whilst maintaining signal. Right, so integration time is the single knob that a space instrument designer can turn with relatively little cost. Remember, the other things are like making a bigger telescope. Nobody wants to do that. Turning down the sun, nobody wants to do that. Right, but integration time is something you can tweak. Okay, so this is raw spectrometer output. So somebody mentioned it earlier. That curve has the shape it has in part because that's kind of the shape of this mixture of tungsten and halogen light lamps heated up to the temperature that we're heating up to. What do you expect is going to happen to that curve? So people had a look at this. So I've got a series of greys here going from white to black with increasing darkness of grey. What's going to happen when I move that to the next grey?
Probably the same shape but lower intensity.
Right, so where are we peaking at the moment? 60,000. So, right, same shape, right? But we're peaking at 45,000. The next grey. If you can't see these, you can come closer. The next grey. So we're currently peaking at 45,000. 25,000. And now I'm starting to see these lamps a little bit. And then when I go to black, right, so basically the black is absorbing most of the light that comes out of the light layer of the spectrometer, and therefore not much is being reflected, and therefore the spectrometer is a measurement. I've still got a little bump there, right? See, I've got a little bump at around 740 nanometers. And that's basically the fact that the light is radiating way more photons at 740 nanometers than it is to either side, which explains the shape of that curve, right? But again, this gets back to that thing. If I want to work out the chemical composition of these things, I've got to use a different variable than emitted and reflected light. Okay. So what's going to happen if I put this on the blue? How do you expect that curve to change? And I should point out, right, this isn't perfect, right? As soon as it's heavier on that end because this is pulling it down. When I push that down, I get a bit more light, so bear with me on that. From 200 to 1100, it's kind of coloured it in there, the visible spectrum that our eyes are sensitive to. So this spectrometer is making measurements from about 200 to 1100 nanometers, and below about 440 our eyes are not sensitive, so this is invisible light to us. Beyond about 660, 680, 700, that light is invisible to our eyes, but the spectrometer can measure it.
So that tiny bump right before 400, is that just like one of the detectors maybe being a little hot or something, or is there?
It could be noise, or is that where one of those mercury features were? Does it go away if I do that? Oh no, yeah, it could be a noisy detector. Yeah. So So this gives me the opportunity to average adjacent pixels to beat down that kind of noise, but we're not going to do that because that's reducing our spectral resolution, right? Because the dispersion of light across the array is what gives us the spectral resolution of about 1 nanometer. So if I move it to the blue, how is the shape of that curve going to change?
There's gonna be decreased counts in all wavelengths except around 450.
Okay, so what we're saying is, because that appears blue to our eyes, that means that whatever paint that paper is covered in is very, very good at absorbing photons which are not blue photons, right? Therefore, pretty good at reflecting photons that are blue photons or have a wavelength of about 4500 nanometers, and we can convert that to an energy using Planck's function. Not Planck's black body radiation law, but Planck's law. Okay, right, so we have a look. So we'll put it on the blue. So there's a bump in the visible blue, right? Well, there's that huge peak at around 820 nanometers. But we can't see that, right? Because that's invisible to our eyes, that's in the infrared. So what we're really seeing is that bump in the blue, right? Which means your hypothesis holds, right? Now, I turned the integration time down on this so that we didn't saturate. We're saturating on a highly reflective target, but this blue is much darker, right? So even for the same input of photons, I haven't changed anything associated with a lamp. The amount of light that the spectrometer measures is lower because this is a dark blue, right? And we also have that blue peak imprinted on it. Now I can make that look a little bit better to make you feel a little bit better by increasing the integration time. So if I make the integration time. Right, so I got a bit more of a bump in the blue. Okay. So what you said holds, at least as far as the visible spectrum is concerned. We've got this big peak in the infrared, but if we're interested in measuring visible light, we don't care about that. What that's telling me is the paper is very good at reflecting infrared light. Okay, all good. So I'll set this back. Well, actually, we'll stick on this. So what if I move this to green, what am I going to see?
More in the 550, less than everything else.
Right, so again, the wavelength, this is visible green, which is photons of about 550 nanometers wavelength. Convert it to an energy, convert it to a frequency. I should see a peak in the green, right?
Yeah.
Okay, you see the rest, so what this is overall more reflective, right? You know, if you look, this is a bright green, not a dark blue. So everything went up and I started saturating in the near infrared. I have a near infrared peak, which is telling me there's something about this paper, or the pigment, could be the paint, which just reflects at infrared wavelengths, right? But I've got a peak there in the visible green, and what was a peak in the visible blue disappeared, right? So that's why it looks green to our eyes. I've got another green over here, which is kind of a dark green. Alright, so I've still got that peak in the green, right? But the reflectance in the infrared has fallen off a lot. But all good, I've got a peak in the green, which explains its colour. How about the red? Should be easy now. Right, so that hump is going to move to the right. And remember, we don't care what's happening in the infrared as far as our interpretation of these colours. Right, so we have kind of flat in the blue, flat in the green, which means that paint is really good at absorbing those photons. And it reflects the red ones, and now we're completely saturated. How do I make yellow?
There will be a peak in the green and a peak in the red.
Right, so I need photons reflected at visible red and green wavelengths and not in blue. Okay. Right, so I'll turn the integration time down a little bit. So let's go back to 125. So yeah, right, I've got a ton of reflectance in the visible green and the visible red, and not so much in the visible blue, and that's why it looks yellow. And if I go back to white, you'll see And now I've got reflectance in the blue, green and red, which is why it looks kind of white. And then I've got a whole bunch of other colours. We had those,
Light blue,
you want the light?
the gray, the steel blue or whatever
This
you
one?
call it. No, but
This one?
yeah. Been dying to see.
Okay. So it's kind of a dirty, that's like a grey, right? If you think about it. Remember I said, here what we're doing is we go from white to black,
Yeah.
with greys in the middle, right? The shape isn't changing that much, it's just kind of the tallness or shortness of the shape. Basically for grey I'm getting kind of equal and constant, equal amounts of red, green and blue. That blue is kind of greyish, so that's why it's kind of flat in the visible part spectrum. Pink is a mixture of blue and red, right? So I don't really have a good magenta colour. Let's see what that looks like. Right, you see there, I've got more in the blue than I have in the green, and then more in the red. So I make magenta by mixing red and blue. Right. So is this making sense when making spectral reflectance measurements, and we can interpret them in terms of the colours we see and the spectra we see. Okay. Okay. So what are we going to do now? We're not going to bother with these, although which out of these colours, which is the closest blue? Somebody want to pick a blue? Which of these is the closest in blue to that blue?
Maybe right there, or maybe on the right. Maybe that one.
That one? I tried to do these yesterday. Oh, how about that one?
Yeah.
Maybe.
Oh, you can try it.
So that's what blue looks like printed out on my crappy printer. And then let's see if we can get this blue.
Not bad. No, not as much.
Blue. So it looks like I've got more red in that signature than I have in that signature, right?
Since we don't care about infrared, should we, or would it be beneficial to increase exposure time so that we can see the blue peak better?
Right. So that's part of this performance modeling thing that we're going to do next in October or November, whenever we're going to meet up again. So you're right. So the way that works is, as a mission designer, you don't design to the worst case scenario, right? So if I say, oh well, if I look at something really white, then I'm going to saturate, so I need to turn down the integration time. But I'm rarely going to look at white stuff. Right? Most things I look at is dark. The Earth's average albedo is 30%. Right? So if that's what I really care about, then I need to optimize my integration time to observe that. Right? So in this performance modeling exercise, we're going to choose a target and we're going to optimize the system design to make the signal to noise ratio the best it can be for the thing that we care about. So you're absolutely right, in this design process, and that would come from the science traceability matrix, right? The scientist says, in order to work out how Mars works, I need to make really, really great measurements of this particular mineral. And then you tune the integration time so it makes really, really good measurements of that mineral. Now what happens in mission design is, NASA doesn't spend $700 million to study one mineral. Right, so you've got a science team with like 30 people on it or something like that, and they all have different science questions they want to answer. And you usually find that by the time you've gone through this process, the instrument ends up being a kind of jack of all trades and master of none, right? Because it has to accommodate all of the science questions. But you're right, you optimize for what you're interested in. What time's Peter coming? Midday or something?
12.
Okay, so we yeah, we're going to actually make a reflectance measurement. So we'll just get through it, and then you can have a break when Peter shows up, right? Have a 10-minute break. So I'll just show you a couple of these. So as I said, these were a few $100 each, and I've got right. So that's a green one. So I've got green and I've got green. Right, I've got green that cost me nothing. I've got green that cost me a few $100 for the whole thing, and then I've got this green that cost me a few $100 for the one. So if I go from green to green So it looks green, right? And it's not a whole lot different than that. The reason we use this is that, and the reason why these are a few $100 each, is that I can go and buy these in a company called LabSphere, and they send me a thumbstick. You can order these calibrated or uncalibrated. Calibrated means they will make a measurement in their lab of how much light this reflects using a super expensive spectrometer, not one that costs $7,000. And they will send me a test report, and they'll show me that spectrum. And in that way, it's calibrated. So if we have a calibration source, so if I'm building a spectrometer and somebody at Brown is building a spectrometer, and we want to make sure our spectrometers are telling us similar things, I can put that in a mail and send it to Brown, and they can make their measurements, and then we can agree that our instruments are producing similar results. This is pretty stable over time. I mean, you don't want to touch it, but if you touch it, you just use some wet sandpaper just to rub off the surface. This thing's okay for a few $100, but you know, this isn't going to last forever, and this is going to change over time. Okay, so these are kind of expensive because they're kind of stable and they can be calibrated in a lab. Okay. Do people remember there was one of the Mars rovers, to calibrate the information that was coming out of one of the Mars rovers, the cameras, occasionally they would look at a target which was a load of colours painted on the surface of the rover, right? Because if you imagine, here's another reason, if that spectrometer starts going a bit weird, if I point it at this and I know this isn't changing, then every measurement should be kind of the same, plus or minus the noise, right? But if I point at this on day 1 and I get a spectrum, and then I point at this on day 100 and I get a different spectrum, which is outside of the noise, then I know there's a problem with my spectrometer, right? So on one of the missions to Mars, I can't remember which one it is, they had targets actually on the rover which were like these color targets, and they calibrated it at JPL. So they say, okay, when we look at that, this is the spectrum we get. And then on the surface of Mars, they would occasionally look at these targets and say, do I get the same spectrum? Do I get the same spectrum? And in that way, you can work out if the calibration is drifting, but you can also work out a correction to get it back into shape. One of the problems on Mars was that their color targets were getting covered in dust, right, over time. So they had a technique which involved using electromagnets, because the dust is made out of iron and magnesium, which are magnetic materials, right? So they had an EM field which they could apply, which tried to get the dust off the target. Occasionally nature would do it, and they'd have a dust storm or something like that, which would get rid of the dust. But that's two reasons for calibration. If I'm looking at the same thing and it isn't changing, my spectrometer better be giving me the same result, because otherwise I just can't do science. So, okay, so the next thing we're going to do is we're just going to make a reflectance measurement, right? And if you remember, one thing we said with the reflectance measurement is, let's just look at how we defined it, right? So we said a problem with using radiance is that depending on the amount of illumination that strikes the surface, we're going to get a different amount of light reflected, right? This cosine of the angle thing. So, what we do instead is define this variable called reflectance, which is just the ratio of the light coming in, striking the surface, versus the light that goes out. Okay. So I'm measuring this, right? This is what the spectrometer is measuring on the outbound spectrometer, right? It's measuring the number of photons that get reflected from whatever I put it on. The light coming in, I also kind of know that, right, because it's coming from the lamp. So it's fixed and constant. But I don't know it yet. I mean, they send you a rough-ass curve that shows you the composition of the light coming out of this thing, but it's not, that was only $2,000, so it's not super stable. So what I'm going to do is use another measurement to work out what the amount of light striking the target is, and in that way, I can normalize out and I can convert the curves I've shown you into a reflectance curve, which looks something more like those peaky and trophy type things that we've been looking at. So the way we do this is, Okay, so a lot of this stuff's automated in this one. So I'm going to do reflectance. Add to that position next. Okay, so I've got this little window in here. Okay. So I'm going to take one of my reflectance standards and I'm going to take my white standard. Right, so this is the white standard. Right. So this is white because all wavelengths of light really, really well. Right. At the wavelengths that we can see with our eyes. Right. I'm just going to show you what the actual reflectance of that is, and it looks like this. So that is the calibration curve that came with that material. So this is what they measured in the lab. So reflectance on one axis, wavelength on the other, and as agreed, this is the wavelength, this grey bar is the wavelength over which that spectrometer is sensitive. Right? So it's pretty high and flat, right? This is only between 90% and 100, so it reflects 99% of the light that falls on it. And this is kind of flat. Right? Not so good here, down in the extreme shortwave visible blue. So that's very good at reflecting light, and it reflects it equally, and it's very well characterized. You'll notice it isn't as good out at longer wavelengths, right? But that's okay, because this spectrometer is only looking in this part of the spectrum. But the key point, that reflects nearly all of the light that falls on it over the spectrum, over the wavelength interval that we care about, right? Which in this case is 200 to 1100 nanometers. So I'm going to first make a measurement of that because that's my reference. Right? Now, if this thing reflects all of the light that falls on it, and I get a spectrum that comes out, what is that spectrum? Kind of a weird question.
Wait, say that again?
If I shine light onto this white thing and I know it reflects basically 100% of the light that falls on it at every wavelength, then what's that spectrum telling me? Here's another way. What's that spectrum telling me about the light I shine on it?
Oh, it's going to be the same as the...
It's going to be the same, right? So that measurement is telling me the spectrum of light which comes out of that light source, right? Because it's reflecting, that material is reflecting all of the light that falls on it equally well all wavelengths. There's a little bit of noise in there, right? It's ever so slightly better, but that's a pretty good approximation, right? So I'm going to make that measurement first because that's my reference. Because remember, on my reflectance calculation, one thing I need to know is how much light strikes the surface, right? So that measurement is going to tell me how much light comes out of the spectrometer. So I make that measurement first. So this is currently on top of just this graph. So if I put my standard there, and then I've got that on there. Can somebody just come and just put a finger down like that? Because otherwise it rocks, right? And it goes. So if you just want, you can, all good, right? Actually, don't cover the hole. You can just put it there. Right, you're good. Can everybody see? Right. So this is now telling me how much light that target is reflecting, right? And the lamp isn't changing. What do we notice about that signature? Saturating, right? I'm saturating because too much light is coming into the spectrometer from that target. Okay. So how am I going to solve this problem? Integration time, right? So what I'm going to do here is, this has an automatic way of doing it. I could tweak the numbers, but it just has a feedback in it. If I click automatic, it will work out. There you go. And it was optimized. So the integration time went down from 124 to 125 to 84 microseconds, milliseconds. Okay. Okay. So now what I'm going to do is, I'm not going to. Don't change anything. You just move the sun. So I'm not going to do any averaging or anything like that. The only thing I'm going to do is, right, here's the first thing. First thing I have to do is collect the dark spectrum. So a dark spectrum is how much light does that thing tell me it's measuring, even if it's measuring no light. And this is basically just the noise in the system, right? So what I'm going to do on that is be careful not to turn the light off. There's a shutter in this thing, so watch what happens to that curve. I'm just going to flip the shutter. right, and it goes flat, right, so I just turned off the sun. And the variation you see, so this is intensity count, so it's telling me that I am measuring a digital count of about 1900, even though no light is coming in. And that's just the noise level in the spectrometer, right? So first what I'm gonna do is gonna make a measurement of that, because I have to subtract that from all of the subsequent measurements that I make, right? That's fake light that doesn't exist in the system. So I have to characterize it and then subtract it from all of my future measurements. This is not quite a flat field, but astronomers use often flat field images to just get rid of noise. So, and it's imperative that you don't move. Okay. So we will do our dark spectrum. Dark spectrum is installed. I turn this on. No need to know what that means. Right. So I've done that and that. Now I go to next. Now, honest, don't move, don't move, don't move. Right, so the next thing I'm going to do is store this reference spectrum, right? I want to know how much light is falling on all of my targets in the future, right? So what I'm going to do is make a measurement of the light that comes back from that target, and we just optimize the integration time. So the first thing I have to do is make sure I open the shutter. Right, so it doesn't matter at the moment, it went back up, right? So now I'm going to make my reference spectrum measurement. Okay, that's my reference spectrum, right? So now I go next, and then it makes me do another background. Close the shutter again. And then I finish. Right, so now what it's doing, you see the axis just changed. I've still got wavelength along this axis, right? But I've gone from counts to reflectance on this axis. I've gone from 0 to 65,000 to 0 to about 100, right? So let's open the shutter again. So at the moment, this kind of makes sense, right? I have no light admitted to the spectrometer, right? And it's telling me reflectance is 0. Now I've got all this nonsense down here. This is basically noise. If you remember that, the lamp isn't very good at radiating light at those wavelengths. The spectrometer isn't very sensitive at those extreme shortwave UV wavelengths. You notice I've also got some nonsense here, right? This goes real high, which is just noise in the instrument. Okay. But this makes sense. I'm not looking at any light and it's telling me no light is being admitted. So if I open that shutter, you will be seeing the reflectance from the white standard. What will happen to that reflectance? It will go up to about but we're in a different space now, right? We're not in counts anymore, we're in reflectance. So it will go up to about what number?
100%.
About 100, and it should be kind of flat, right? Because what we'll be doing, we will be dividing the light that comes from that by itself. 2 divided by 2 is 1. 3 divided by 3 is 1. 100 divided by 100 is 1. So here it's 0 to 100, not 0 to 1. But we're dividing its reflectance by its reflectance, which is 1. Right? So if I flip that, okay, so it's a little bit more, which probably means you moved. So let's just try and repeat it quickly. It was a good job though. You did a good job. Right, we'll try and do this again. Right, so we'll do a dark. shutter. Standard. Next. Dark. Next. Finish. Open up the light again. Okay. Right, so it's kind of 100 and flat all the way over, apart from our noisy parts of the spectrum where the detector doesn't work very well. Okay? Good effort. You must adjust, maybe you put your finger over the hole or something, because if I do that, and here's another thing, I got to do these measurements in the same way, right? So if I do this, right, so the measurements of the standard and the target have to be made in the same way, right? So I'm dividing by it from itself, and that gives me a value of about 100. Okay. So now, if I go back to these targets, so this is white, and it looks like that, but it's actually not reflecting as much light as my white standard does, right? It's reflecting about 90% of the light. Let's see what happens when I go to blue. Okay, so again, ignore that crap on the left, but I've got a big spike in the blue, and I've got a trough in the green and the red, and then I've got this plateau out in the near infrared, right? If I go to the green, spike in the blue. Yellow is a mixture of green and blue. Right? So I'm now making reflectance spectra, and as long as I don't change the light source, then if this doesn't change and I go back and measure this in 100 days, it will give me the same spectrum. Right? So this is really all we're doing. All that stuff I've been talking about is what we've just been going through now in class about making a measurement. And a lot of the terms, integration time, things like that, how we are actually going to design instruments which are way more expensive than this to make these measurements. A common application of this kind of work is vegetation. So I will, to normalize, and that's the spectrum of this desk. So if I flip this over, leaves can be a little bit transparent, so I want to normalize the background. So if I take my living leaf and my not very good shaped leaf and then my terrible shaped leaf. So I'll show you, we'll look at this in class from space. Right, so that's why healthy green vegetation looks green, right? This needs to photosynthesize and create plant matter. You need carbon dioxide, which it drags from the atmosphere. You need water to provide nutrients, and you need energy, right, which comes from the sun. The energy is absorbed by pigments in the leaf called chloroplasts. Those chloroplasts selectively absorb visible blue and red photons, and that drives photosynthesis. They reflect visible green photons, not because they want to, but because they don't need to, because they're absorbing enough energy in the blue and the red region to power photosynthesis, right? So that's why healthy green vegetation looks green to our eyes. What do you notice about the infrared reflectance of vegetation?
High.
High, right, really high. Now we don't see that, but that's an evolutionary thing. So if plants are absorbing, well, plants tend to be kind of dark green, and they are reflecting at most 20% of the light that falls on them, right, in this part of the spectrum. If I shine light on you for a long enough period of time, what's going to happen to you?
It'll heat up.
You'll warm up, right? You're absorbing these photons and they convert it to heat. What happens to creatures if you just heat them up for an indefinite period of time? They die, right? You know, proteins denature, etc., etc. So the way plants have evolved to overcome this, they need to absorb energy, visible light, to grow and live. They dump the extra heat by, if you like, by not absorbing light in the infrared part of the spectrum. Right? So they have high reflectance in the infrared part of the spectrum, and depending on the plant, it can be much higher. But by not absorbing light in the infrared, that's how they've evolved to kind of keep their temperature kind of low. They also transpire and things like that, and that's a structural thing. That's basically they have this spongy cell structure, which has lots of index of refraction boundaries, gas cells filled with gas, and the high incident, like a foam on a pint of beer, the high ratio of index of refraction boundaries in that spongy gas-filled cellular structure to absorbing material, which is the walls of the cells, means that we get effective first surface scattering from the volume, which gives us this high infrared reflectance. What's going to happen if I look at the dead leaf?
Probably
it's-
less green,
It's going to look kind of brown, right? So how do we make brown?
more red reflecting, and a little
Right.
bit less green.
Right, so we're going to take yellow as a starting point of mixing red and green, and we're going to say orange is close to yellow and brown is kind of close to that, right? So we're going to expect reflectance in the red and the green, but not so much the blue still. Right? And that's kind of what we got, right? We got slope down from red to blue. What happened to the near infrared reflectance? I don't have this really steep increase. You see that increase from 680 nanometers to 740 nanometers? That's called the red edge, and it's diagnostic of vegetation. Nothing natural looks like that apart from vegetation. And when vegetation no longer photosynthesizing, we no longer have those chloroplasts absorbing visible red and visible blue light. That red edge collapses, and that's one of the diagnostic ways that people use satellite remote sensing to spot changes in the health of vegetation on the surface of the Earth. And then if I go to yellow, and that kind of makes sense, right? All of a sudden, I've got this big spike in the visible green part of the spectrum. So if I take my healthy leaf, I have a spike in the green, not so much in the blue, not so much in the red. If I go to my yellow leaf, now I've got a load of reflectance in the red, right? And the reason for that is that the leaf is no longer absorbing red photons, right? And the reason for that is that the absorption is being taken over by things called xanthophylls, which are things that, and beta-carotenes, which are things that make carrots look orange, right? Basically, the effect of the chlorophyll is being masked by the effect of these other pigments because the leaf is no longer healthy. And that's why I'm getting reflectance in the visible red and the green, which is causing this thing to look yellow. So this is just an example, you know, just by making these repeated measurements, I can work out something about vegetation health. Okay. One last thing I'll show you quickly. Right, so this doesn't look like any of the other targets I've shown, right? Kind of got most of our information out around 840 nanometers. This is a thing called dysprosium oxide. Anybody know what it is? I don't know what it is, right? We use it as a wavelength calibration, right? Because again, this is a material that exhibits absorption peaks and troughs which correlate with its chemical composition. And I don't care what they are. What I care is I have peaks and troughs along the whole spectral range. So what I can do is say, well, I've designed a spectrometer and I want to check that it's working, right? So I put this underneath it, and I say, well, okay, this thing is reflecting, you know, a ton of light over here, but I have these absorption troughs, these reflectance troughs, right? And you can see there are a few on the right-hand side there which are especially prominent, right? So based on its chemical composition and the calibration of this before they shipped it to me, I know exactly what wavelength those absorption troughs are supposed to take place in, right? So if I build a spectrometer and I compare my measurement with the reference and the troughs are at different spectral locations, different wavelengths, then I know my spectrometer isn't working right? And I've got an offset in the wavelength calibration, which I can then try and fix. Okay. So again, this was one that I made yesterday in my office. Same setup. This is the measurement of that target, and again, we've got noise here, so it's crap. And we've got noise here, so it's crap. But this is the measurement I made in the lab. This was the calibration measurement that they sent me when they sold me that thing. And you can see that this feature looks like this feature, and this feature looks like this feature, and this feature looks like this feature. right? So it's just telling me that the spectrometer is still healthy and still working. And in 200 days, I should be able to replicate this measurement, right? And if it's got more noisy, or if the spectral location of these pulses has moved, then I know there's a problem with my spectrometer, right? So this is a reason when you launch instruments into space, you tend to have onboard calibration, right? You tend to have a target on the spacecraft that the camera can look at and say, I know what I should be measuring from you. Am I still measuring that signal, right? And if you are, then great. If not, then the people on the ground have to work out a fix to recalibrate the data. Because otherwise, if I look at the same thing time and time again, it's going to change, even if it's not changing. Or if it is changing, I won't know it's changing because I can't trust my measurement, right? Okay, we're done, Peter. So we're going to have a break because I've been going on for ages.
Yeah, we're taking a break right now, but
Yeah.
I need to find,
Eric. Okay, so see you in 15 minutes or something like that. So I hope that was useful.